All right, here we've got another work energy problem that involves a pendulum or a swinging type change in energy. So Jane, whose mass is, I changed it to 75 kilograms. It turns out actually that's not going to matter in the end. But she needs to swing across the river. The river has a width of D. It's filled with man-eating crocodiles, and she has to save Tarzan from danger over there. However, she's got to swing into the wind on a vine having a length of 16 meters and initially make an angle of 31 degrees with the vertical. So that's this. That's the 31. And then she's got to swing an additional 16 degrees to the other side. That's 16 degrees over there. Now, if air resistance is negligible, so if there is no wind, and Jane starts from rest, how fast is Jane going to be moving when she gets to Tarzan? Well, that is a traditional energy problem. We take the energy, let's call this position A and this position B. The energy at B plus any work done between A and B will equal that energy at B. Well, there is no work because air resistance is negligible. There's no rockets or external forces that are non-conservative acting. So whatever she's got at A is going to be whatever she has at B. So here we know her velocity at A is 0. She starts from rest. But she's got some height we got to worry about. Now where are we going to make height 0? But anyways, so she's got potential energy of gravity. There's no spring. There's no kinetic energy. That's it. She's got that potential energy of gravity at A. And that's got to equal everything at B. Well, she gets to B. Is she going to have height at B? I think in the case of this pendulum, I'm going to make this the lowest point of the swing, the 0 height. I'm going to make that H is 0. So she's got a non-zero height at B, a different height at B. So there is a height at B. So we're going to say it'll be that. There is no spring, and we're trying to find out how fast she's moving, so I assume there's going to be kinetic energy at B. Since that is the energy due to motion, it will tell us how fast. All right, so this is mass of Jane, G, height at A, is going to equal the mass of Jane, G, height at B, plus 1/2 the mass of Jane, velocity of Jane at B, squared. So as often happens in these energy problems, same mass for all the terms, so we can divide everything by m, and it turns out the mass does not matter. Whether it was Jane or somebody else swinging across, they would have the same speed at the end. The tricky part here is what is this height? So we did this before in another video. So we took 0 down there. So this orange thing, that's the height at A. That's the height at A. Right? Because that gets me there. That's the height for A. But the B is, we'll see this blue marker. It's just this little thing right there. Right? That's my height at B. So I've got to figure those out. And you might recall how we figured that out. Is we took the entire length of this rope. The entire length of that. Which is also this. And we could calculate the cosine of that. We could calculate this section right there, and that was L cosine theta when this right here is L, right? That right there is L, the length of it. So that HA is L, the whole yellow part, minus L cosine theta, is how we figure that out. So let's write that all down there. So HA, I got a capital H up there, is L minus L cosine theta at A, this theta. Because again, this green portion is the L cosine theta. This whole yellow is all of L. And I just want that orange, so I want the yellow minus the green. The whole length minus that, whole length minus that. That's H at A. And likewise, H at B, pardon my handwriting, is L, is the whole. And then this section here is L cosine theta at B. So L minus L cosine theta at B. I'm going to put that all symbolically in here and see if anything like reduces out for me. G, I can factor out that L. 1 minus cosine theta at A is going to equal G. Again, I can factor this L out. L 1 minus cosine theta at B plus 1/2 V at B squared. Okay. Move this over there to that side and multiply by 2. So we got a G L 1 minus cosine theta at A minus G L 1 minus cosine theta at B is going to equal 1/2 VB squared. Can we clean this up somehow? Right? If we take this whole big thing, we can factor out the GL, and then we got all that junk in there. So we factor out the GL, we got a 1 minus cosine theta at A minus 1 minus cosine theta at B. So it turns out that change in height is just this little portion here, which is the difference between the green, L cosine theta A, and this pencil line, that's L cosine theta at B. So the L cosine theta B is larger, so there is a minus, so it ends up being, when you do the algebra, the ones cancel. You're subtracting this negative, so that becomes the positive. It's cosine theta at B minus cosine theta at A. And again, that is this little portion in here between the orange and the blue. That little portion. That's the change in height. We can move the 2 over there, and that's VB squared. And now you just plug in your numbers, and you get the answer for that. But knowing how to show that process and work that out, find that height, that can be a little tricky geometric thing. So for mine, 2 times 9.8 times 16 times the quantity cosine 16 minus cosine 31. It's 32, and square root of that, 5.7. So I get that the velocity at B is 5.71 meters per second. So finding that change in height, or the heights at A and B, is what's important to solving that for that velocity. Now, part B, it turns out Jane just makes it to Tarzan. What does that mean? That means the velocity at B is now 0. Calculate the work done by air resistance during the swing. Well, the energy at A plus the work between A and B, which is due to air resistance, is the energy at B. Now, though, we've got that potential of gravity at A, because it's up high. We've got the work of the air, and that's going to equal our energy at B, but now it's not moving at B, so there's only UG at B. Only that. So to find that work of air, the work of the air resistance is going to be equal to U potential at B, potential energy at B minus potential energy at A. And you have those terms up there. in what those are equal to. So can't cancel out the m's now because this doesn't have an m in it. Right? We want that work of air. We've got an mgh at B minus mgh at A. The m's do not cancel out now because the work of air resistance does not have an m in it. Can't cancel it out. Got to keep it. So expanding all that out like we did here before, here again we subtracted. This was pretty much the difference in the potential energies. Add an m in there. Move those over. We did a lot of that work. Here the difference in the potential energies gave us the kinetic energy. So following that same outline of work, we've got mgl 1 minus cosine theta b minus 1 minus cosine theta a. That is going to equal our work of air. Equal all that. Again, these ones cancel. We flip things around, and you get mgl cosine theta a minus cosine theta b. And you can work that out, plug that in with those numbers, and you find that work. You'll notice it comes out negative, and it should come out negative because the air is removing energy from the system. The air is not adding energy. That would be positive work. The air is removing energy. So the air is doing negative work on Jane. All right, that should make it really easy for you to solve, but hopefully you can apply this to other situations in the future. Have a great day.